Following slide is going to show you what are the self-diversity, intrinsic diversity, and interdependability. What's the relationship or correlation between this diversity and the direct coefficient L11 and coupling coefficient? Yes, so let's take a look on the first one is the self-diversity. So for the self-diversity, that is like we measure, the material system we're talking about is the homogeneous chemical. It's a chemically homogeneous materials, right? So the component I and so how to measure the self-diversity? Based on your knowledge, you know the concentration along your materials are uniform, right? So it's very difficult to us to measure the self-diversity. So people will use the radioisotope I star to label it, and then we can measure the diffusion profile of this I star. Then you can get the self-diversity of these materials. So this is how people get the exactly measure or get the self-diversity of specific materials. But now your system, you have the component I and I star, right? So this kind of because you have two components, and you also can consider this will be as a result, because this diffusion, some kind of, you can consider this is as a result of random work process to reach the homogenization of I star during diffusion process, right? This diffusion process, right? Okay, so just keep in mind, you ended the I star, but there's still no spatial variation in chemical concentration. That means the concentration of I plus I star, you also can keep it at the certain value. So there's no spatial variation in chemical concentration. So the concentration of I plus I star are uniform along your materials. But there do exist a spatial variation in chemical potential, because the chemical potential of I and I star definitely are different. So there's exist a spatial variation in chemical potential. And as long as you know, as long as there's a variation in chemical potential, so that must have a driving force, right? To drive this diffusion or this kind of mixture between I and I star. So this process driven, actually some people will say that the driving force probably is a chemical potential gradient or a variation in chemical potential, or you can call it like the increase of entropy in the system during the this diffusion or mixture process. So as long as you ended the isotope labeled I star, then you create a system that will result in variation in chemical potential, and finally that will help the system to diffuse or mixture well to increase the entropy. So after a serious deviation, we can get the self-diversity in this chemically homogeneous system can equals to KT, and the direct coefficient L11 divided by concentration C1 minus the coupling coefficient L1 star 1 divided by C star 1. And the detailed deviation can be found in page 14 in the lecture notes. But how to before you reading the lecture notes, I probably should give you some background reference to help you to can understand how we get this, how we derive the self-diversity. So the background knowledge is we call the network constraint. The network constraint actually states that when you change in one component, the changes in one component leads the changes in other components in the system. then if you summation of all atoms or all components, the changes of all components from I equals to 1 to NC should be equals to 0. So here you can consider that if you have a pure material, and in this pure material, because volume already be fixed, so the available crystal lattice point is fixed as well. So the total number, if this is pure material, is called material A, the total number of atoms plus the vacancy, the numbers of vacancy, definitely is equals to what? Equals to the total available lattice point in these materials. So if you have more atom A's located at crystal lattice site, then you will get less vacancy shown in the lattice point. On the contrary, if you have less atoms A occupying the lattice point, then you will get more vacancy at the lattice point. So the summation of the atoms and the vacancy should be equals to the total available lattice point in your materials. This is example. So this is what we talking about for is the atom and the relationship between atom and vacancy. The other example would be something like the chemical reaction. You use the reactant A reacted with reactant B. A plus B equals to AB, right? So the total numbers of A atoms must be the same, right? If you got more A, then you got less AB. If you got less A, then you got more AB. The summation of this should be the summation of the changes of A and AB should be equals to 0. So that is some in this kind of situation, we are going to use this network constraint. And based on this network constraint, do you just remind you that's energy conservation law we mentioned in lecture 1 is the thermal energy equals to the change in thermal energy equals to the change in internal energy plus the change in mechanical work plus the change in non-mechanical work. This we call it the chemical potential work. Okay, so if you also always summation the component 1 to NC, then we can separate this term into these two terms. And sorry, I forgot to correct this one. Is I equals to 1. So you can divide it by these two terms, right? Is component 1 to NC minus 1, and you ended the NC term here. And NC term, don't forget you need to times the chemical potential, then you can get this term equals to this term. And in order to, and we don't know the value for the this chemical potential NC, the NC. So we are going to find which term can substitute this term. So we got this one to the NC plus summation I equals to 1 to NC minus 1, the NI equals to 0. Then we can just simply move to right-handed side and times the it should be times the minus mu NC. Then you got this term, right? And this term, if you have a look on this one, so it will be minus mu NC, the NC is like this one, right? So you just substitute this term here and combine both of these terms, you got this. So you compare this and this, you have some idea. This is a potential difference between the I and NC, right? And the example we just raised is, we just show you is the atom A and the vacancy. So in the pure materials, what's the driving force? For pure materials. the driving force for material A in pure material can be written as the minus chemical potential gradient, and the chemical potential will be the mu I minus mu vacancy, if you consider NC as a vacancy, right? So the driving force is the minus gradient of relative chemical potential of component I respect to component NC, and NC here can be considered as a vacancy here. So let's use the same idea to take a look on the lecture note. In order to get the self-diversity D star D, then we need to, first of all, we need to write down the flux and force equation, right? And now what we have here is we have materials. We have one material, one atoms and radioisotope label star 1 atom. So the driving force here can be the atomic flux of atom 1 directly driven by F1, and this is a coupling term, right? And the J star 1 directly driven by the F star 1 and coupling, also indirectly driven by F1. Then when we try to write down the driving force here, you can base on previous slide. The driving force here is the chemical potential gradient, but gradient with what? Respect to the vacancy. And also just so minus chemical potential gradient respect to vacancy. And the second one is also the driving force here will be the mu star 1 minus the vacancy. You can use the same idea to write down and get the J star 1. And the boundary condition here would be, don't forget, the first one will be the net flux passing through specific plane, it should be equals to 0. So the J1 plus J star 1 plus J vacancy equals to 0. And this the other used for information or knowledge is the concentration 1 plus concentration star 1 is isotope level 1 plus the CV concentration vacancy definitely equals to A is let's tell you the total concentration of all components should be fixed. And based on this, and there's a only very important assumption states that the vacancies under thermodynamic equilibrium will be thermodynamic equilibrium locally. The mu v can consider equals to 0. Based on this, you directly drop these two terms or this mu v out, and you got the chemical potential gradient is proportional to the concentration gradient of atom 1. And based on this boundary condition, you take the gradient operator on this equation, you will get this relationship, right? Because this is constant, so nothing related with the gradient with the length. And this is also, we consider the uniform vacancy concentration along your material. So when you take a gradient, you can directly drop both this term out, and you got this. So now you have some idea about what the relationship between the concentration gradient of atom 1 and the concentration of gradient of star 1. So you simplify, use this term and converted chemical potential gradient with concentration gradient. Then you got this term, right? And we also have the relationship between the star 1 and 1. So you substitute and you get this relationship and take the concentration of atom 1 out. Then you got this, the flux J1 can be expressed like this. And as you know, we assume that the vacancy flux can be considered equals to 0 because it is uniform vacancy concentration alone in your materials. So the J star 1 equals to minus J1. So J star 1, why is it so important, the J star 1? Because the self-diversity is a D star D, right? So J star 1 can be written by minus star D concentration gradient of star 1. As long as I can convert it or substitute J1 also expressed like this, so the rest of part we can that would be equals to the star 1, star D. So this is how we play with, right? So the J1 expressed like this, right? You just copy it here, just copy J1 here, and converted the concentration gradient of atom 1 by using this equation to convert it by concentration of star 1 and compare these two results, then we can know the self-diffusivity D star can be expressed like this, is the KT, direct coefficient, divided by C1 minus coupling coefficient divided by C star 1. Okay. So now you have the idea about the self-diffusivity is related to the intrinsic material property, mass transport material property, right, is a direct coefficient and coupling coefficient. Okay, so let's move to what's the intrinsic diffusivity. The intrinsic diffusivity actually is when you measure the atomic flux while you stand at the interface in the materials. Then you divide it by the minus concentration gradient, then the diffusivity you get would be, we call it as intrinsic diffusivity. So this example is we show is the diffusion couple 1 binded with 2, and we consider we have this material system. And don't forget you are going to use the network constraint. That means use some summation of the flux of all components should be equals to 0. And if you consider this diffusion couple, we assume J1 is larger than J2. So this must be a vacancy flux toward to left-handed side to balance the atomic flux of atom 1. And where, because we are going to stand as the interface, so where is this, which directions of this interface moves? So based on this, you know the J1 is larger than J2. That means let's more one atoms move to right-handed side. Let's going to push this interface toward to left-handed side. So some people call the interface is moving to the upside direction of the flux or faster diffusion component. Yeah, for toward this direction is upside direction of J1, right? And J1 is the fast diffusion component. Okay, so after series deviation, you also can get the intrinsic diffusivity D1 can be expressed like this. And if you take a look on here, there can be considered as two parts. The first part is similar to the self-diffusivity, is KT times direct coefficient divided by C1 minus coupling coefficient divided by C2. Similar with the self-diffusivity we derived from previous slide. And the second term is interesting because it's 1 plus this term. It's a partial log gamma 1 divided by partial log C1. So gamma 1 is we call the activity coefficient. This coefficient actually defined by thermodynamics. As I hope you remember or have some idea. The A is the thermodynamic activity equals to gamma X. X is atomic fraction of atom I. So A equals to gamma Xi, and as you know, Xi can be expressed like the average atomic volume times the concentration, right? So this one actually, the value for the gamma is to describe the ideality of the solutions. So just give you a quick review here. So let's we call it Henry's law and Ross's law. Ross's law is here, and Henry's law is a deviation from the ideal solution. So we define the A thermodynamic activity A equals to gamma X, right? And also can be expressed like the vapor pressure after mixture divided by the vapor pressure before mixture. And this gamma is a function of temperature and also the composition. that means X. If the gamma equals to 1, that means this solution belongs to ideal solution. At these conditions, A, because this equals to 1, so A equals to Xi. So if you plot the A nickel versus the atomic fraction of nickel, if it is the ideal solution, then it will be obey the Ross law. It's a linear relationship. If it is ideal solution, gamma equals to 1. But however, if it is deviated from the Ross law, we call it a non-ideal solution. So probably the gamma will be larger than 1 or smaller than 1. So if gamma larger than 1, this larger than 1, that tell you the vapor pressure after mixture is higher than before, the vapor pressure before mixture. So the P prime larger than P0. So that tells you after mixture, that means the AB attraction force definitely is smaller than AA and BB attraction force. And this is smaller, so that will cause the vapor pressure increase because the force is the magnitude of the force is decreased, so that will result in the increase in vapor pressure. At this situation, this attraction force is larger, right? And larger attraction force tell you the energy is more negative. More negative, that means if the system tend to be AA and BB together, that will decrease the free energy of the system. So in this kind of case, it will go into phase separation. That means A tend to bind with A, B tend to bind with B. So the system is going to go to the phase separation. But however, the other case is, how about the gamma smaller than 1? If gamma smaller than 1, that tell you what? The gamma smaller than 1, that tell you the vapor pressure after mixture is smaller than before mixture. So the AB attraction force definitely is higher than AA and BB attraction force of AA and BB. So this is the attraction force between AB is larger. Larger means this energy will be more negative to allow to decrease the free energy of the system. So the system is going to be the AB alloy or AB compound. So this is just a quick review, tell you that as long as gamma is not equals to 1, that no matter is gamma larger than 1 or smaller than 1, this curve is going to, the gamma is going to change with composition, right? It's going to change with composition. Gamma is a function of composition. If the gamma equals to 1 is ideal solution, so the gamma is not the function of composition. Okay, so you have this idea. So let's move back to the results we got here. So the second term is related to the thermodynamic activity gamma, activity coefficient gamma, and partial with log C1. And that's the other term we call log omega, log average atomic volume, partial with log C1. And as you know, the average atomic volume is not going to change with concentration, so you can simply drop this term out. And we also assume the direct coefficient. The direct coefficient term is larger than coupling term, so you can ignore the coupling coefficient term. We assume the coupling term is smaller than the direct term, so you also drop this term out. To simplify this case, then this intrinsic diversity of A term A can be expressed like this term times this thermodynamics activity term, and this is related to the ideality of the solution, right, of the mixture. So this term you can consider as the self-diversity D1 star. So D1 star, so D1 intrinsic diversity of atom 1 can be expressed like the self-diversity star D1 times the term we call it is a thermodynamics factor here. And probably some people will consider why, because we also assume the direct coefficient effect is larger than coupling coefficient term. So based on this, the star D1 self-diversity of component 1 can be expressed like this. So you can write down D1 intrinsic diversity can be expressed like this, right? And if we, as we mentioned, if gamma equals to 1, that tell you that it probably is ideal solution. That means the mixture is ideal solution or the dilute dopant. Then in this case, gamma equals to 1, and gamma is not going to as a function of concentration, so you can drop this term out. Okay, so at this situation, then D1, this intrinsic diversity will be equals to self-diversity D1 star. Okay, so just a remind the ideal solution. What's the ideal solution means? Non-ideal solution. So that means actually when this is the interaction between A and B, other interaction between A and B equals to A and B and B. If ideal solution, that means before mixture and after mixture, no matter A is be surrounded by B or A is be surrounded by B or A is surrounded by A, there's no any difference on the bond strength, attraction, anything. This kind of situation we call it ideal mixture of ideal solution. But usually it's not going to happen, right? Because A, B are different atoms. The bonding energy definitely different. So in reality, most kind of mixtures between A and B is either obey is usually either gamma larger than 1 or gamma smaller than 1. So can be deviated from, definitely is deviated from Rose's law. It's belong to Henry's law. Okay, and you only can predict by Henry's law when you still have a dilute dopant, right? Dopant something. Okay, so this is extra knowledge. Hope you can have some idea about the what's the ideal solution and non-ideal solution. Okay, so let's move to the last diversity. We call it is interdependability, and you stand in the lab and you observe. You can measure the atomic flux, and you directly divide it by the minus concentration gradient. Then you can get the interdependability as we mentioned before. Then I give you these two examples to hope we can explain more clear on the difference between the crystal frame and the valence fixed frame, or you call it is in the crystal frame versus a lab frame. This is also a diffusion couple, 1 bonded with 2, and we try to plot the concentration profile of atom 1 by using the blue curve. And in this case, J2 is larger than J1. So based on this, you have idea the interface is going to move toward to right-handed side with velocity v, right? And if you are interested in, if we're talking about in the crystal frame, that means you stand on or stand in this interface, right? And during the diffusion, you are going to move with the interface. And based on this, at this interface, you can observe the flux. You can observe how many atom 1 passing through this interface. And this is the not total number of atom A passing through this interface. So the J1 can be expressed like this, J2 is expressed like this. This is what we observe in crystal frame. But if we stand outside our material system, you need to do some modify on the flux you measured J1 prime. Because what? Because the plane also moves. In addition to the flux passing through this your interface, there's extra atoms passing through this interface because this interface moves toward to right-handed side with the velocity v. So in order to that, we need to do some we need to add the extra term here to describe the J1 prime we measured at the lab coordinate. So it's a C1V. Some people will ask about what's the flux, why flux can be expressed as C1V. If you check the unit, it's correct. And we also mentioned in the page 2 or 3, or probably 3 or 4, flux can be expressed equals to CV and also CB, right? And also equals to what? Mobility, concentration, driving force, right? Okay, so now you got the J1 prime, and you use the same concept to get the modified J2 prime. Then based on the volume fixed concept, and you put you use this relationship, and then you can, after series of deviation shown in the page on the page 16 in lecture note, and then you can get the J1 prime can be expressed like this. So I need to explain what's the volume fix. That means J1 prime is the flux, how many atoms passing through this interface, right? And if you times the omega 1 is the atomic volume of atom 1 plus the J2 prime times the omega 2. Actually, the idea is during the per unit time, the volume of atom 1 move to right-handed side will be equals to the volume of B, or the volume of atom 2 move to left-handed side. So that will allow this material is not going to move toward to right. So it's we call a volume fix because the volume of your material system already be fixed. So let's show how many the total how much total volume of atom 1 be moved to right-handed side should be the same magnitude of volume the volume be moved on the atom 2. So this we call a volume fix relationship. Okay, so after series deviation, you can get this relationship and have a look on here. So we know the J1 prime can be expressed as minus this term concentration C1, concentration gradient of atom 1, and this term we call it interdivisibility. And this interdivisibility is related with D1, D2, and also atomic fraction of 1 and 2. And also J2 prime can be expressed like minus this term interdivisibility times the concentration gradient of atom 2. So remember for this one, interdivisibility, for a diffusion couple, we only have one value of interdivisibility for one material system. So in this one, no matter to describe J1 star or J2 star, we only have one interdivisibility. But however, in previous line, we have two. If you have two material, right, then we have two intrinsic divisibility of two different types or kinds of atoms. Okay, so based on these results, we make some assumption. If X1 is very small, that means that it's a dilute dopant or ideal solution. This X1 is very small, we can drop this term out, and X2 is approach or equals to 1, and interdivisibility will be equals to D1 is we call intrinsic divisibility. And based on previous slide, we also know if it is ideal solution or dilute solution, our intrinsic divisibility will be equals to self-divisibility. So if summary, if it is a dilute solution, ideal solution, the intrinsic diversity equals to self-diversity equals to intrinsic diversity equals to interdiversity. They are all the same value. Okay. So this slide just remind you that the volume fixed relationship we just mentioned. Based on the net flux equals to 0, then we got the volume fixed relationship, something like that. Okay, so today we're going to end it here, and next week we are going to start from the Kirkendall effect.